Section 4.1 is about some basic probability ideas that are going to carry forward through when we talk about some more specific distributions a little bit later. So there are a bunch of definitions up here at the front that we kind of need just to sort of be able to talk about anything probability-wise. So an experiment is any kind of action where you get an outcome. And a random experiment is one where you don't know which outcome you're going to get. So there would have to be at least two for that to make any sense. But assuming that there are at least two possible outcomes, a random experiment is one that before the experiment happens, you don't know which one you're going to end up with. So then your outcomes are your possible results. Sample space would be the set of all possible outcomes. And then an event, you can have two different types of events. You can have an event that just consists of a single outcome, which would be a simple event, or one that consists of multiple outcomes, which would be a compound event. So for flipping a coin, you can't really have a compound event, really. I mean, it's either going to be heads or tails for your outcomes, right? So for your outcomes for flipping a coin, we're going to have heads and tails, or H and T. Because a lot of times this is written without words, just with some sort of symbol. And H and T seem like the most logical symbols for heads and tails. And then if you're going to write it with H and T, then the sample space S would just be the set consisting of H and T. Because your only options when you're flipping one coin would be either that you get heads or you get tails. Then the next one that's sort of the most straightforward example that we can start with, I think, would be rolling one six-sided die. Because then with the sample space, you could get a 1, 2, 3, 4, 5, or 6, right? Those are your possible options when you roll one die. So those are going to be the outcomes that are in the sample space. So 1, 2, 3, 4, 5, and 6. And then let's say if event A is, we'll make these compound events. So we'll say rolling an even number. So it's a compound event if there's more than one way to do it. And here there are three outcomes that are going to work, right? 2, 4, and 6 are all even. So if we were going to write out what A is in set notation, it would be the set consisting of 2, 4, and 6. Then how about for event B? I could make it odd, but that seems too obvious. How about rolling a prime number? That's a little bit different at least. So for B, we'll say rolling a prime number. So then B would be the set consisting of, and if you look up at the sample space here, the prime numbers in there are 2, 3, and 5. So 2, 3, 5. All right. Then what about rolling 2 dice instead of just 1? Well, the sample space gets kind of big, because then you say, well, you could have a 1, 2, 3, 4, 5, or 6 on the first die, but also on the second die, which means that you're going to have 36 possible outcomes here, right? If you're, I guess, differentiating, this is what the first die is and this is what the second die is. So with your sample space, then this is going to be kind of hard to write out, but it's going to be 36 since you have 6 outcomes for the first die and then 6 for the second, so 6 times 6 would give you that. But I think the easiest way to write this would be with ordered pairs. So like if we're going to do that, then our sample space would be, and I guess we could start off with 1 on the first die, 1 on the second die. So that's how I'm thinking about the ordered pairs. So just telling you individually, first die, second die, what you end up with. So you could have 1, 1, 1, 2, and so forth, down to 1, 6. And then kind of systematically going through it, we say, well, what if you get a 2 on the first die? You have a 2, 1, 2, 2, up to 2, 6. And then you could say, well, then what if you get a 3 in the first die? What if you get a 4? What if you get a 5? What if you get a 6? And ultimately, at the very end, where you're going to end up is with 6, 6. So you would really have 36 possible outcomes here, but I can't really write all that in. Right, I clearly don't have the space for it. But you'd have 6 outcomes where you get a 1 on the first die, right? Because then you could get a 1, 2, 3, 4, 5, or 6 in the second. Then you have 6 outcomes where you get a 2 in the first die, 6 where you get a 3 in the first die, 6 where you get a 4, 6 where you get a 5, 6 where you get a 6. So you end up with 36 possible outcomes. But let's say, just to have some compound events here, what if event A is rolling a sum of 10? Because you can do that in more than one way, right? Like you could have 5 and 5, right? Since 5 plus 5 is 10. 4 and 6, that would work. 6 and 4 would work. But really that's it, because anything else, you would end up needing a number that's too big to show up on a die, right? Like you can't have 3 and 7 because 7 is too big. So what you would end up with for your event A would be 4 and 6, 5 and 5, or 6 and 4. Right? So there are 3 different ways that you can end up rolling a sum of 10. And then for event B, how about instead of a sum one, maybe something like the same value on both dice. So you get 2 1s or 2 2s or 2 3s or 2 4s, that kind of thing. So then B would be the set consisting of 1 1, right? 1 on both dice, 2 2, 3 3, 4 4, 5 5, and 6 6. So there are 6 different ways you can get that. All right, then the next thing, here's another definition of what a complement is. So if S is your sample space and A is some event, then the complement of A is everything in the sample space that's not an A, all the other possible outcomes. So like for these, like for this A right here, just to say it in words, if A is rolling a sum of 10, A complement is rolling a sum that's not 10. So it's everything else. And then event B, if B is rolling the same value on both dice, B complement would be rolling different values on the 2 dice. So anything except for getting the same number both times. So if you want to think of the complement as sort of like the opposite of the event, that's true. Like it's the opposite within the sample space. And there are a few different ways to write it. Our book uses the bar on top. I reflexively write it with like a C, like a superscript, like where an exponent would go. But they're both valid, so I'll stick with the bar over the top to make things match up with our book. So for those, well, I guess actually it's not for these, it's for the second one. So I guess then this is the third one. So the second one is rolling 1 6-sided die. What are A complement and B complement? Well, if we go up here, I think we can see them. So event A was rolling an even number, and if the sample space is 1, 2, 3, 4, 5, and 6, A is 2, 4, and 6, then A complement is going to be rolling an odd number. And then it's just going to be 1, 3, and 5, right? It's the other options that aren't in A, the other possible outcomes. So then A complement, so A bar, as a set, that's going to be 1, 3, and 5, because really what that would be in words is that it's rolling an odd number. And then let's see, B, so that's rolling a prime number. So I guess rolling a non-prime number. This one's a little easier, I think, just to look at what numbers are missing. So we've got 2, 3, and 5 in there. The other numbers that are in the sample space that aren't 2, 3, and 5 are 1, 4, and 6. So those are the ones that would go in B complement. So B complement will be the set consisting of 1, 4, and 6. So I guess in words, rolling a non-prime number. All right, and then what happens if your event is equal to the sample space, right? If it's everything, well then the complement would have to have nothing in it, and that's what you get. So then the complement of the sample space is the empty set, denoted either by the brackets with nothing in between, so a very literal interpretation of empty set, or this, where it's just kind of like a circle or an oval. It's really supposed to be more like a circle, but that one looks a little stretched out. It's supposed to just be like a circle with a diagonal line through it, right? Like on a road sign, like when you can't make a U-turn, red circle, diagonal line. Kind of like that, except that the diagonal line comes out of the circle instead of like being contained within it. But it's that kind of shape. Let's see, we got some properties down here. So the probability of any event has to be between 0 and 1, because 0 would be the probability of an event that never happens. 1 is the probability of an event that always happens. So you couldn't have anything beyond that, right? You couldn't have something occur less than never or more than always. So those things don't make any sense. But events with probability 0 would be things that could never happen. So like here, rolling a 15 on a 6-sided die, you're never going to get that. Or probability 1, it's something that always happens. So with a single 6-sided die rolling a number less than 10, right? You're always going to get 1, 2, 3, 4, 5, or 6. Those are all less than 10. That's always going to happen. And then the probability of an event plus the probability of its complement would have to be 1. Although usually the way that you end up using that is more like this, where you end up having to maybe solve for the probability of the complement. So like if the probability of A is 0.65, then the probability of A complement is 1 minus 0.65, which is 0.35. That's the kind of thing you usually end up having to do with that property, the one that involves the probability of an event and the probability of its complement. Okay, so the next thing in here is, well, we can do a little bit with piecing together, like, all right, this is what this event would be in terms of its outcomes if we had it written in words, or if this is what an event is, then we can figure out its complement if we know the sample space. But how do you actually figure out probabilities? Because that's what this is ultimately supposed to be about. There are a few different ways to do it. And it kind of depends on what sort of event you're looking at and what sort of experiment you're looking at, really. So classical probability, all the stuff that we've had so far, like flipping a coin or rolling a die or rolling 2 dice, use classical probability for that. And like it says down here, this approach works if all simple events are equally likely. And that's the case, right? If you're going to roll 1 die, then the chance that you get a 1 is 1/6. The chance that you get a 2 is 1/6. The chance that you get a 3 is 1/6, and so forth. So the simple events are just rolling a 1, 2, 3, 4, 5, and 6. And yeah, all their probabilities are the same. And that's going to work for things like rolling dice, flipping coins, gambling games like roulette, playing the lottery, that's going to work, right? Like with the lottery balls, they're going to have the same probability of showing up. So that's when you can use classical probability. So then in order to figure out the probability of an event A, then what you would need to know is the number of simple events. And then for event A, you'd have to figure out, okay, well, within that, how many different ways can you get this event to happen? It could be more than one, right? Like if you were going to roll 2 dice, rolling a sum of 10, we said there were 3 different ways that you could do it, right? So we said that event A, so if that's rolling a sum of 10, we said this can occur 3 ways, right? So we already have this down from before. So this can occur 3 ways. So then if we were going to write this as a set, we'd have, and this is just from before, 4, 6, 5, 5, and 6. Oops, I forgot. Left parenthesis. There. And these are the simple events. Just knowing, okay, if you're going to roll 2 dice, you get some number on the first die and some number on the second. So as far as the sample space was concerned there were 36 simple events, right? So I guess we'll have that too, that S consists of 36 simple events, right? This was a thing we'd already figured out. So then the probability of A would end up being 3 over 36. And that's because there are 36 simple events, right? If you just roll 2 dice, then there are 36 things that can happen where you get some number on the first die and some number on the second. And then, well, out of those 36, how many of them are going to give you a 10? 3, right? The 4, 6, the 5, 5, and the 6, 4. So there are 3 different ways that event A can happen. So that's how you get the 3 in the numerator out of 36 total simple events. And this fraction actually reduces, because this would be 1/12. Or as a decimal, if you'd prefer it that way, 0.083. All right. Well, then the second example, and this one we can't really recycle stuff. If a coin is flipped 3 times, what's the probability of obtaining 2 heads? Okay, well, there is kind of a systematic way to write out the sample space here, which is to kind of go by how many heads you have. So I guess I'll go 3, then 2, then 1, then 0. Right? With 3 flips, that's how many heads you could have. So this would represent getting 3 heads in a row. So head, 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 right? Then what about getting exactly 2 heads? Well, you could do that by having a head, then a tail. Or a head, then a tail, then a head. Or a tail, then a head, then another head, right? Those 3 ways you could get exactly 2 heads in the 3 flips. And then what about getting exactly 1 head in the 3 flips? You can say, well, then it could be the first flip or the second or the third. So if it was the first flip, you'd have head, tail, tail. If it was the second flip, you'd have tail, head, tail. And if it was the third flip, you'd have tail, tail, head. And then the only other option is no heads, which would just be 3 tails. So tail, tail, tail. So there are 8 simple events there. And so then how many different ways can we get 2 heads? Well, it's these 3 right here that have exactly 2 heads, right? So there are 3 ways that you can do it. So then the probability of 2 heads, it's going to be 3, since there are 3 ways to do it, out of 8, since there are 8 simple events here in the sample space. So that's 0.375 as a decimal. So that's one way of doing it, of figuring out what the probabilities are, the classical approach, but that's only going to work if the simple events are all equally likely. What if that's not true? You got to do something else. So another option is this. So empirical probability, so the idea there, if it's empirical, is that it's based on collected evidence, right? Or this is also called a relative frequency approximation. But these are the same thing. So relative frequency approximation, empirical probability. Those are 2 names for the same idea, which is that whatever experiment you're interested in, if you're trying to figure out how likely it is for a certain outcome to occur, you just repeat the experiment over and over and over again. And then whatever outcome or whatever event you're interested in, you see how many times that happens. And then from there you can say, okay, well, when we repeated that experiment over and over and over, event A happened this many times out of this many repetitions of the experiment. And then that's how you would get your relative frequency approximation. So it's like these examples here. So for that first example, it says 200 glass bottles were dropped from a table 3 feet high onto a tile floor, and 142 of them broke. So based on that data, what would be the probability of a glass bottle breaking when dropped onto a tile floor from a table 3 feet high? Well, let's see. I guess we would just call this maybe probability of breaking. That sounds reasonable. So in the repetitions of the experiment, 142 broke out of 200. And you say, okay, well then we got our 200, our number of repetitions, and we got the event to occur 142 times. So 142 divided by 200, which is 0.71. That's going to be our empirical probability here. All right, maybe for one with numbers where the division isn't quite as smooth, So a study of 750 business administration graduates at Toledo revealed that 441 out of them were not employed in their major area of study in college. So for example, somebody who majored in accounting now being the marketing manager of an e-commerce firm, right? So they're still in business, but they're not an accountant, right? So they're doing something a little bit different, not their major area of study. So what would be the probability that a particular business graduate would be employed in an area other than his or her college major? So I guess this would be the probability of other area or other field or something like that. I'll just say other area since it says area in the wording. And then let's see. Here the repeated experiment is just kind of checking an individual graduate to see what kind of job they have and what their major was before, right? So that happened 750 times, and out of those 750 times, 441 times, it ended up being the case that somebody majored in something different than what they were doing for a living. So that's going to be 441 divided by 750, which works out to, at least to 3 places, be 0.588. All right, so then this one is not, right? Not employed in their major area of study. But what's the probability that they will be employed in their major area of study? So I guess we can say the probability of being employed in their major area. Well, it's one or the other, right? Either they're employed in their major area of study or they're not, right? There are only 2 options, which means that the probability that they're employed in another area is the complement of the probability they're employed in their major area. So then we can say, well, if it's the complement, then this would have to be true, that the probability they're employed in their major area is 1 minus the probability that they're employed in some other area. So then we can say, well, this is going to be 1 minus 0.588, which would end up being 0.412. All right, so that one, it doesn't come right out and say that it's a complement, but then you think about it, you go, well, it's one or the other, right? Either they're employed in their major area or they're not. So it does end up being a complement problem. All right, then how accurate are these empirical probabilities? That's another thing, right? You think, well, okay, fine, you can derive an estimate or an approximation just based on repeating the experiment over and over again, but how good is that approximation going to be? Well, it kind of depends on how many repetitions you can do, because the more repetitions you can do, the better your approximation is going to be. You're going to get a more precise estimate. So like it says here, the more repetitions you've got, the closer the relative frequency probability or the empirical probability would be to the actual one. So basically bigger is better in terms of the number of repetitions. So just for an example, like suppose you flip a coin 10 times. What you'd expect, like what would be the most common possible result before you start doing the flipping is 5 heads and 5 tails. But if you get something that's a little bit off, that's not weird, right? You get 4 and 6, that's not weird. You get 3 and 7, even really that's not weird. Not with only 10 flips. But 3 out of 10, that's not going to be a very good estimate, right? Because at least here we know what we're supposed to get, right? It's flipping a coin, we're supposed to get 0.5, right? We're supposed to get half and half. But the more that we flip the coin, the better the estimate's going to be. So look at what's happening here. This is supposed to illustrate that as we go from 10 flips to 100 to 1,000 to 10,000. So with 10 flips, we had 3 heads. We go, all right, 3 out of 10, that's 0.3. That's not weird for 10 flips, but that's not a very good approximation of that probability either. All right, how about 100 flips instead of 10? Let's say we get 64. So 64 out of 100, that's 0.64. Okay, that's better than this, but it's still not that great. 1,000 flips, we got 517 out of 1,000, so that's 0.517. All right, now we're getting better, right? That's getting closer to 0.5. And then 10,000, let's say we get 5,021 heads out of 10,000 flips, 0.5021. Right, that's pretty close, right? Like, so as the number of flips goes up, the closer and closer we're going to get. That's the idea of the law of large numbers. So large number being better in terms of the number of repetitions, because the more you got, the better your probability estimate's going to be. All right, then another kind of probability, and this is one that's really just for specific cases, more or less, like things that you couldn't repeat. And the thing that I would think of that would be the most common is weather, like the chance that it's going to rain, right? Like any one individual day, you can't repeat, right? Like there are going to be other days historically that have been similar, but you can't repeat one day exactly over and over and over again. So that's where subjective probability comes in. So for events that can't be replicated easily. So weather would be one, right? You can't replicate the same day over and over and over again, like Groundhog Day, right? Like that's not a thing that we can have. Or Palm Springs. I guess I could update that movie reference a little bit. But then if you can't replicate the event, then you can't really use classical probability, and then how are you going to use the empirical probabilities either, right? Like you kind of need easy replication for that. So it relies on a person's judgment, and different people may not get the same things. And you actually see this with weather, but usually the weather predictions aren't that different, right? Like you'll see one prediction that says 20%, one that says 30%, right? Or maybe on a day where rain is expected, like one will be 80%, one will be 70%, right? You never see like where one's 80 and one's 30, right? Like that's kind of crazy. But usually they're pretty close to each other, even if they're different. And so weather is one thing where this comes up a lot. Another is with health, the chance of something happening like a heart attack. So like if a doctor tells a patient the probability of a heart attack is 35%, and then what would that be based on? Well, like their current health, their medical history, right? I mean, like it's going to be things like that, right? It's going to be like, okay, well, based on other people who had a similar profile, like this is what I think your chance of having a heart attack is, right? Because you can't replicate that one person over and over and over again and see how often they have a heart attack, right? That's not a thing that's possible here. And then same thing with the weather, right? If you can't replicate one day exactly, then you say, well, we have historical data where we have similar situations where, it's this time of year and where there's a storm system is in the same general area and the storm system is similar to these other ones in the past. Then, right, from there you can kind of come up with an estimate. So subjective probabilities, right, there is a basis for where they come from, right? It's not like the numbers just sort of appear out of thin air. But they can vary from person to person because different people can interpret historical results or similar patients, things like that. Different people can interpret those a little bit differently. So you don't always get the exact same number. All right, then this idea of having an unlikely event, this kind of goes along with when we talked about the idea of having something unusual or significant before, like in the last chapter, things that were more than 2 standard deviations away from the mean. If you have a bell-shaped distribution, being more than 2 standard deviations away from the mean will basically line up exactly with having a probability less than 0.05. So this is more or less the same concept. It's just now we're talking about it in terms of probability. But it's still that idea. So an unlikely event, we're going to consider that to be one with a probability less than 0.05. And here's another law of large numbers idea in a way, whereas the number of hands, which would be like a repetition of a blackjack game, as that goes up, then things that are a little bit off are going to become unusual. So if the probability of an average player winning is about 0.46 in an individual hand, then you can say, well, in 5 hands, if somebody won 3 of them, you go, well, that's 60%, right? That's 0.6. But that's not that weird, right? It's only 5 hands. You're going to get a lot of fluctuation there, right? I mean, sometimes you get 2, sometimes you get 3. Once in a while you get lucky, you get 4, maybe you get 5 if you're really lucky. But then, okay, well, the probability of an average player winning 3 times in 5 hands, it's 0.284. So that's really not that weird, right? That's saying that if you played 5 hands of blackjack and the probability of you winning one individual hand was 0.46 and it always stayed 0.46, then the probability of winning 3 times in 5 hands happens about 28% of the time. You go, all right. Like, that's not going to happen all the time, but that's not that weird. Like, that wouldn't raise suspicions, right? But then in 40 hands, the probability of an average player winning slightly more than half, 21, it's 0.089. So that's about 9%, right? 8.9%. All right, well, because then you say, well, this actually is a lower percentage than this one, right? Because this one's 0.6. This one is, what, 0.525, I think? So, yeah, that's lower, but also we're playing more hands. So now that difference from 0.46, there's not going to be as much variability generally with more hands being played. But you still go in 9%, that's going to happen once in a while. All right, well then 51 wins in 100 hands. Now we're getting into rare events. And why is this probability coming out so low now, to where now it's considered unlikely? It's because the number of hands went up so much, right? Because now we're up to 100 hands. Like for blackjack, that's kind of a lot, right? To sit there and play 100 hands in a row. If somebody won 51, like they're doing pretty well, right? Because they'd be expected to win 46, right? 46% of 100 is going to be 46. So yeah, then they're doing pretty well. And it would be kind of unusual to win that many. But then with 500 hands to win 251 there, so just to get a little bit over a half, that's really, really rare, right? That's less than 1%, right? Because that's 0.6% if you want to think about it in percent form. So that's one that would be really rare. That's somebody running very, very hot. And I think that's one where you'd think, that's so rare, that's probably going to attract the attention of like the casino manager. Right? Because that's one where it's like they're taking a loss here. So that's where they'd probably be looking into the cameras, making sure that nothing unscrupulous is going on. But you know, the point here is really the reason these probabilities are going down, even though really the proportion of wins is also going down, but it's still staying above a half. It's because there are so many hands being played. Essentially what happens is the more repetitions you're going to have, so here are the more hands of blackjack, the amount of variability goes down. And when that happens, like just the amount of natural variability is going to go down, then when you get something unusual, it's rare. Right? Whereas if you only have 5 hands, you get something that's slightly unusual, that's not weird because there's a ton of variability. But the more hands you play, so generally the more repetitions you have, there's going to be less variability. And so then there are going to be things that come back as, you know, looking kind of unusual. Even though when you look at it, you go, well, this is barely above 50% versus 46%. That doesn't seem that weird, but it becomes weird with enough repetitions. So that concept basically feeds into sampling variability, which is a big thing that shows up later in the course. So I guess this unlikely events part, in a way, this is kind of foreshadowing what comes later more than just being specifically a thing for section 4.1.